Hi, my name is Gloriana Moua, and I did my undergraduate research at Cal Poly SLO on the comparison of concrete slender wall software with full-scale experiments. So a quick presentation overview. I'll go over my project goals and the purpose behind this research, and then I'll go into detail about the full-scale testing, the results from that testing, and the impact that it had on future provisions. And then I'll compare those results with current design software, and then I'll have my concluding summary. So my project goal was first to understand ACI design provisions, and then I wanted to try to duplicate the test results in multiple different software programs, analyze and compare those results and see if the software varied from the original testing. I wanted to try to pinpoint user assumptions within the programs that may have caused the results to differ. And then lastly, I wanted to see which of the software programs could have been contributors to the discrepancies within the engineering community. The purpose behind this project, and I think the purpose of all engineers, is to make sure that the designs ensure life safety and to understand that current design provisions are empirically derived from experimental full-scale testing. Current design programs may deviate from ACI provisions with a more theoretical analyses that might not match experimental reality. And it's important to understand the behavior of slender walls and all designs before using software programs so that users are able to spot when there are misalignments with provisions in the original test results. Here are some photos of some tilt-up concrete slender walls, just for reference. So the testing was done from 1980 to 1982, and the reason for this is because there had been an increase in concrete masonry walls due to the economy and architectural appearance, fire safety, and ease of construction. And along with this increase, there was also a desire to make the walls slenderer to reduce cost. So what were the goals for this testing? They wanted to try to analyze the behavior of these walls when subjected to both lateral and eccentric axial loading. And the results showed that the fixed limitation that once stood for the height to thickness ratio was not necessary for the design of these walls, and that each of them should be based off of strength and deflection, including P delta effects. So here's the setup from the testing. You can see that the lateral loading here was supplied by an airbag that was the width and height of the wall, and the lateral pressure in pounds per square foot was measured through the use of a single tube manometer, and the vertical loading was applied at an eccentricity of half the wall thickness plus the ledger length, and that was supplied with a load drum. Each of the panels, I focused on the 12 concrete, specifically 2 out of the 4 thicknesses, the 9.5 and 5 3/4 inch thickness. And each of them were 4 feet wide with a clear span of 24 feet. Here you can see a load deflection curve from the 2 panels that I analyzed. And this near vertical line that you can see before the breaking point is the panel performing as an uncracked section. Here, where it starts to bend, is the cracking load. And afterwards, you can see a significant increase in horizontal deflection with little load being applied, and that is because there is a stiffness reduction. Here are pictures from the actual testing. On the left-hand side, you can see the deflection, and on the right-hand side, you can see cracking patterns. You can see, if you look closely on the left-hand side, there's a slight gap between the wall and the airbag, and this actually raised some concerns about potential results. So in 2006, a summary report was created by the SEAOSC Slender Wall Task Group to try to take into consideration that contact area concern and incorporate adjustments into the results. But as you can see from this graph right here, that before yield, right here, before cracking, the behavior was almost exactly the same. And no adjustments were actually made as this issue only concerned loads that were above yield. So ACI 318.19 section 11 discusses the alternative methods of out-of-plane slender wall analysis. And this is these are the equations and calculations that I used to do my hand calculations to compare to the original testing. Something to note about ACI is that the modulus of rupture of concrete, FR, you can see there, is used in ACI as 7.5, whereas the original testing used 5. So to account for this, ACI incorporated the 2/3 factor when you're applying to cracked. The factored moment MU is applied at mid-height, and it's due to combined flexure and axial loading, and that can be calculated 2 ways: A, by the iterative calculation, or B, using the direct calculation. And if you look closely at 11.8.3.1c, you can see that they're using I-cracked for the factored moment, so that will affect, later on you'll be able to see the moment plots that I'll show. And then also the service level deflections is also used, calculated using an iterative calculation, checking MA against 2/3 of the cracking moment to see which equation to use. So some concerns. There were concerns that programs aren't aligning with the original experiment testing, and thus could pose safety issues to designs. As technology advances, software programs and modules are being developed to potentially improve or outsmart ACI 318 provisions, but there's been concern circulating within the engineering community that some of these software programs are not aligning with the original testing results. So the ACI Committee 551 questioned whether it was appropriate to stray away from these approved provisions when designing these types of walls, and due to the sensitivity to inaccuracies, it can lead to a quick strength and stiffness reduction, which will ultimately result into large deflections. So I analyzed 3 different software X, and like I said, I wanted to try to duplicate the panel results. So I inputted all of the values from the original testing. And I also wanted to try to find assumptions that could cause differences in the results. So right off the start, I was able to see that users are able to choose the rupture modulus of either the 5 or the 7.5 coefficient. And this could be an issue because the original testing was based off of 5. And this rupture modulus determines when the section is expected to crack. So using the 7.5, you would expect to see the section cracking much later with higher loads. Another thing for users to assume would be this I effective. This specific program used Bischoff's equation to calculate the I effective. So rather than saying the section is uncracked and now it's cracked, it's using this Bischoff's equation to determine how cracked the section actually is. The other option would be I cracked full height, which is assuming that the section is cracked from the start. And then software Y. Software Y I looked at, and when I was running my analysis, I noticed that there were some unusual behaviors in the program. And when I looked into it, I realized that it was due to this stiffener cracking coefficient. So how I realized that it was unusual is because I was able to apply up to 300 pounds per square foot of lateral loading with no cracking behavior. And based off original testing, that was not the behavior that would be expected at that high of loading. And so when I looked into it, I found that this stiffener cracking coefficient is the default input, but after the initial run, it's up to the users to calculate iteratively the cracking coefficient and then manually put them into the program in order to continue their design. This could be an issue if users didn't know it was their responsibility, and it could make it to where they would believe the wall could take more loading than it actually did. So then software Z I looked at, and another issue that I see was that as the lateral loading increased, I noticed my out of plane deflections in the diagrams tab of the program were much lower than were expected at that loading. And so when I did some research, I found that that actual diagrams tab didn't show P delta effects, and that the actual deflections that I was looking for had to be found within the report section. And so this can be concerning if engineers are using this software, and they didn't know that that value needed to be pulled from the report. And this would be a case where engineers would base their designs on out-of-plane deflections that did not include P delta effects, and that could significantly affect the behavior of the wall. So some comparisons, I compared my load deflection curves. In the orange line, you can see are the actual values, and then the dark blue line is the ACI provisions. Just something to note is any of the curves that fall underneath the actual results are considered a conservative design, whereas those that are above them are considered unconservative. You can see that just looking at software Y, which deals with the cracking coefficient, it goes straight up, which is expected because this was made with no adjustments to the iterative calculation. And you'll never see this wall crack if you don't change the cracking coefficient. Then you can see software X of the 7.5 coefficient, it is expecting to crack much later than the actual panel results, and that's because of that coefficient. But then if you look at software X, the 5 coefficient, you can see that it's cracking around the same time as ACI, and it's also underneath the actual, so it's considered a conservative design. Here is just to show that if you were to choose I cracked full height within the software X, assuming that the section is cracked from the start, is why you see no immediate stiffness reduction, because it's just a constant deflection based off of loading. And also one more thing to note is that software X uses the Bischoff method, which you can see here with this curve. Here's just some more plots. And here you can see that there's no orange line that represents original testing, and that is because from an analysis point of view, you're not able to change the rebar D distance in some of the programs. And so because this testing had already occurred and the distance was not at the center line, I was unable to compare all of the programs by not assuming that it was at the center line, or by assuming that it was at the center line. So here are some moments. You can see 2 moments. There's a blue portion, which is the primary applied moment due to lateral and eccentric loading, but not including P delta, and the orange represents P delta. All the programs found the primary applied moment appropriately, but there was a big discrepancy within the computations of P delta effects. And then here you can see ACI assumes the section is cracked based off of that equation that I showed you, which overestimates P delta effects. And then you can look at software X, where the 7.5 coefficient, it doesn't think that it's cracked yet, which is why there's no difference in the P delta effects versus primary moment. When you're looking at the 5 coefficient, it's cracked, but it believes that it's not fully cracked, using Bischoff's method to see just how cracked the section is. Looking at why there's no change among the 3 panels between MU applied and MU with P delta. And that's because Y knows that the wall is cracked but ignores full cracking. And this program refers to Branson 1964 to find I effective, which is an out-of-date code, and later determined that slender walls do not behave this way experimentally. And so without the stiffener cracking coefficient and referring to out-of-date code, there's the P delta effects are close to 0. And then lastly, if you're looking at the Z, software Z, this has had the most dramatic results when it comes to cracked. You can see that cracked is an option within the program, and there's a serious increase in moment due to P delta effects, simply because the horizontal deflection increases so quickly. But if you're looking at the effective option, users are allowed to choose the effective cracked regarding the moment of inertia for the analysis, and this resembles X's 7.5, also referring to Hugh Brooks, which refers to Branson 1964. This program does not acknowledge that the section is correct yet. Okay, concluding summary. I just want to emphasize that it's important to understand the behavior of slender walls and actually anything that we design before depending on software, because different software will require users to make assumptions, and it's on us to decide whether the assumptions are appropriate and adjust accordingly. And lastly, for everyone to know that software is a tool and can be used incorrectly. And because of this, it's recommended that engineers not stray away from approved provisions. And yeah, that's my presentation.